Thank you. Well, hello, everyone. Welcome to this module on a smart grid course. My name is Hossein Tabatabai. I'm a PhD student here. I'm working on networking, specifically deterministic networking. I'm working with Professor Jean-Yves Lobaudet, who is a co-teacher of this course. And today's topic is an introduction to the TCP-IP. So as you might already know, you are divided in two groups. You are the majority. You are the ones that you hadn't passed a related course, a computer network course, such as TCP/IP. That's why this is an introductory course. For the others, for a few students who had already passed such courses, they have an advanced course in parallel. So for this week and next week, you are known as beginners. So to do the labs and quizzes, go for the beginner part. Okay. Cool. That's the plan of this week. Well, today we have a lecture. Then I will invite you to take the quiz COM-B1. B stands for beginner. And you can start doing the lab COM-B1, which will basically the thing that we discussed today. Regarding the quizzes, a small reminder, well, quizzes are not mandatory. I mean, are not graded, but they are mandatory. Meaning that you have to be up to date with your quizzes in order to submit the lab or go to the next quiz. It's nothing special. I mean, you can see the answer, but the whole thing is to practice the lecture and then go through the labs and so on. Before dive in, during the lecture, we will have such multiple choices quizzes. So I would like to have your feedbacks in the middle of the lecture. To do so, for sure, we would like these feedbacks to be anonymous. So all of you could participate and you don't have to be shy. That's why we use this tool. It's called SpeakUp. You can download the application or you could use the web interface at this website. So also the room key and the website is written on the board. Well, I invite you all to join this SpeakUp app, and this is the room key for this SGT beginner course. Oh, that's a dummy question. It's a bit of background information for me and for you to get smooth with this SpeakUp app. So if you join there, I will open the first poll, and now you can provide your feedback. So what is your section? You are an electrical engineer, computer scientist, management, or other? Well, as I say, it's completely anonymous, so don't be shy. Just participate. It's good for both of us. For the first one, I failed a bit, so order if you want to join. So until now, we have either electrical engineer or other. So what is other? Energy. Okay. So we are switching. Very well. Well, now we can see the result also. Oh, that was a dummy question for you to get familiar with the thing. Now we can dive in. Oh, let's start why we are here, why I'm giving you a lecture on communication. Where is communication in a smart grid? Well, so far you have studied PMU, phasor measure unit length. Well, for example, in a smart grid, you might have PMUs at different locations. These PMUs do some measurements in real time and send these measurements to a control center, for example, here, can be called PTC. Well, this control segment will receive these measurements from different locations and do some analysis on it, make some decision on it, and send some control data to others. That's one example of communication that exists in a smart grid. Another examples are, well, it's a smart grid, like a smart home. You have devices that are connected on each other. They are autonomous, so you have sensors and you have control devices that control each other autonomously. So you need connections there. Well, we have communication in a smart grid. That's why we have an introductory course there. We do not go in depth. We cannot go in depth, actually. Is for you to have a big picture of how things are and a bit of experience of how communication works. Well, that's a plan today. We'll start with the basics, the layered model of communication, and next week we'll go to the program's view and some performance aspects. Well, the TCP-IP or the internet is a layered architecture. Well, there are two important words here, layered and architecture. I will talk about them. When you write a big piece of software, what you do, usually you divide it into smaller pieces. To well-define smaller pieces, you call them functions or modules. And you create some interfaces so that these modules could communicate with each other and the whole program works. You can think of internet as the same thing. So internet is a very large piece of software with a bit of hardware. So what people has done was to create boxes and put them on top of each other. Each of these boxes has a well-defined meaning, has a well-responsibility, there's a well-abstraction. And you put on top of each other, meaning that each layer provides a service to a single lower layer. On internet, we have 5 layers. Starting from the top, we have the application layer. Application layer is nothing but the application that you use. It can be the Facebook app, it can be the Netflix, Spotify, YouTube, even the web interface that you use. So it's the part that we as humans interact with, we as users interact with. So it's the human-friendly part. It helps humans and machines, computers interact with each other. Well, here is, as I said, it's a human-friendly part. For example, we want to send a video on a WhatsApp to your friend. Well, the video is what you understand is really the video. But you need something that network understand. Well, that's the job of transport layer. So the application layer provide this video to the transport layer, and transport layer convert it to a new format that the network understands. What is this new format? It's nothing but a stream of bits or bytes. So if it's a large video at transport layer, we might break this video into smaller chunks. See, we call them packets. So we create a smaller packets that are a stream of bits and bytes, and then this is something the computer understands that it will be forwarded to the destination. Well, at interconnection layer, we have 2 layers. So we have network and MAC. We'll see today why do we have 2 layers. What the job of network and MAC is to connect all devices all around the world. You want to make communication possible for any possible sender and receiver all around the world, no matter where they are, as far as they are connected to the internet. We want to draw a path. This path supposedly contains several intermediate points, but it's possible. That's the job of network and MAC layer. What is this physical layer? So far, what we have, as I said, we have sort of packets. There are a stream of bits and bytes. Now, anyway, there is a distance between the sender and receiver, even if you are in the same room. If my computer wants to send data to your computer, we need some physical things to go through your computer from my computer. That's the job of physical layer, to convert these packets to some sort of, for example, electromagnetic waves, radio waves, or optical waves, or whatever the means that you use. Well, that's an overview of the 5 layers that we have. That's why we call it layered. What does that mean that it is architecture? It means it's a set of principles, a set of rules that we should respect in the internet. It's not how we implement things. There might be different implementation of TCP/IP in hardware or software. As far as they respect this architecture, which is a set of protocols, set of rules, there are a valid implementation. There might be bugs in implementation, but we do not talk about implementation. We talk about architecture, talk about principles. Well, why do we do that? Well, as I said, like software, you do functions because it's more manageable, it's more doable, instead of big, huge things that you could easily get lost in it. Other thing is, it becomes easier to develop things. So when you separate, for example, the application layer from the rest of the internet, you can develop different application independent of the internet. You can have Netflix, Spotify, you can create your own application. As far as you respect this interface between the application and transport layer, it is a valid application. Same thing in other layers. So if you update something, if you change something in one of the layers, if you respect the interface, it is transparent to the whole network. And now we will go through each of these layers one by one. Starting from the first one, the application layer, as I said, is nothing but a layer to help machines and humans interact with. In the simplest case, it involves two computers. For example, we have a user that wants to visit this website, it's the IBM website in Zurich. Whenever this user clicks on this web page, it will send a request to a web server somewhere. In this simple example, it's directly connected to a web server. Normally, it doesn't happen. The web server receives a request. If there is no authentication or security reasons, a simple case, it will provide the data, and the data is nothing but the HTML web page. And then this user could see this web page that she asked for. Within this application layer, we use principles, protocols. What does mean that we use protocol? Protocol are rule of the games. For example, here the protocol is HTTP. It is the rule of the game that the sender and receiver should play within such that this application works. For example, in order to obtain this web page, the user must send a request, and this request must have a specific form. For example, I want to see there is an address, there is some data in it. And if it's, for example, HTTPS, there are security authentication also. And if the request is within this protocol, the server, with respect to some protocols, provides some data. And again, this user must use these protocols to read this data, so to successfully see this HTML page. And as I said, you can write your own application layer. I mean, it's nothing special. You can create very, simple protocols that you respect, and then you can connect to computers that works in a new application layer that you have written. Well, let's go to the transport layer. For example, here it's an example of the mailing application. You want to send a message to someone, and this is what you do in the application layer, right? This is you write the message, you write the destination address, and you click on the send. Then it's up to transport layer to convert it to a new format that computer and network understands. As I said, it might be, for example, in this case, it's most probably one packet that includes your message and some metadata. We'll talk about those metadata. Those are data that you add to the raw data such that it will reach the destination. Well, transport layer provides a programming interface called socket API. We'll see next week, and in the next lab, we'll work with sockets. The good thing about sockets is what you do are very simple things. I mean, you do nothing more than send and receive comments. You do not do complicated things with sockets. In this programming interface, you do send, receive, close, open, and we'll talk about them mostly next week. Well, in transport layer, we have two main protocols that have survived throughout the years in the internet. UDP and TCP. Well, TCP is the one that carries the name of the internet, TCP-IP also. Well, UDP is the least service that you can get from a communication. Well, from a communication, you have a sender and receiver where you want to send some data and you receive them. That's the only thing that UDP for you does. So in the sender part, send the data, send the messages, and then in the receiver, if there is some message to receive, it will receive it. But what's the main difference with TCP and UDP? Well, the main difference is the reliability. TCP is reliable. However, UDP is unreliable. It's not reliable at all. What does that mean? It's not reliable. Well, you should think of an internet as a chaos. So, internet, we do not have reliable connection in internet. When you send some, as I said, when you send some data, you put them in a form of packet and you send these packets. These packets might be lost because of millions of reasons. There is a radio error, there is a Wi-Fi connection error, there is a buffer overflow somewhere in the network. In fact, buffer overflow very frequently happens. Internet is a big queuing system. At some intermediate point, there is a queue that several users are using it, and this queue might be full at some point, and all new incoming packets will be dropped. When you send some packet, it is possible that this packet will be lost and never reach the destination. UDP does nothing about it. So the sender just received the packet, that's it, it's finished. And the receiver might or might not receive it. But with UDP, but with TCP, we care about losses and we recover the losses. How do we recover the losses? Is by doing retransmission. On the internet, I mean, it's not rocket science. Every protocol that we talk about, when you think about it, you are engineers, and you think about it, to how, for example, we could recover losses, it is probably the correct way. I mean, if you look at the internet, you see more or less the same thing has been implemented with a bit tweaks sometimes. Well, how could we recover losses? So we could ask the receiver whether you have received this packet or not. So we force the receiver to send some acknowledgement that I have received this packet. If I receive this acknowledgement, well, I assume that this packet is received and I can move on. If for some reasons I do not receive an acknowledgement, whether the packet itself or the acknowledgement has been lost, I suppose that this packet never reached the destination and I will retransmit it until I receive an acknowledgement. That's how TCP recovers losses. It's a bit more complicated than that, but in few words, that's how it does it. Well, internet is not reliable, but when you have a TCP connection, you see a reliable connection. You see that everything is being sent, is being received, and also it's even better, there's a sequence guarantee. If you send 5 messages consecutively in sequence, you will receive them in a destination with the exact same sequence. That's what transport layer does in TCP. It respects the orders. There is another information. Well, the unit of information in UDP is message. However, in TCP is byte or bit. What does that mean? When you provide a message to the UDP to send it for you, it will use this exact same message. It will do nothing about it. It will put it in a packet and will send it. As I said, when you put it in the packet, it means you add some metadata, for example, the destination address, the source address, and some other important things that make this connection possible, and it will send it. However, in TCP, we do more. We might group several messages into one packet, or vice versa. We might break some message. If, for example, it's a very long data line message, we will break it into smaller chunks, send it over several packets. Well, why do we do that? Because it's more efficient to group some packets together. That's why we care about it in TCP. Well, TCP is a more sophisticated one than UDP. So there are more overheads comes with TCP. The metadata that you add to each packet, they call headers. With TCP, there are more of them because you need to know the sequence number, you want to take care of the losses. So there are more metadata added to this TCP. There are overhead. There are useless data at the end of the day. At the receiver, you remove all of them and you only take care of the data that you are interested in. Well, there are overhead, there are inefficiency. Well, whenever, for example, you have 2 packets that are two messages that are ready to send, it's sometimes inefficient. It's sometimes efficient to group them in one packet. Then there is less overhead. That is done in TCP. Well, as you see, TCP is the more sophisticated one. It provides you more services, but these services comes at a cost. The cost is complexity and some other thing that we will see. Both of them, depending on the use of the application, might be used. UDP and TCP are both usable. I already said that in UDP, we do not recover losses. That's in transport layer. However, the application layer might recover some losses, might do some retransmission. For example, in a case that we want to send a single message that requires a response. In those cases, mostly we use UDP. An example of those we'll see today. Whenever you want to connect to a website, you know the name of this website. You want to connect to apfl.ch, you know the name, but it's not enough to connect this website, you need to know the address that the network understands. It's the IP number that we'll see today. To find the IP address of a website, of a name, you will send a request to a DNS server. It's a domain name server. At those servers, there are well-defined servers that has a mapping between all addresses and all names. And you will ask, what is the address of this website? And those DNS servers will respond to you, well, this is the address. Now you have the address and you can start the communication. That's an example where you send a single message that requires a response. For those things, you'd use UDP. It's much simpler. You want to send only one message. There is no sequence or anything that you care about. Where you send a single message and you wait for a response. If the application does not receive a response, so we assume that the thing is lost. So I need to do a communication. So in the application layer, we ask transport layer to do retransmission. That's one thing that we use UDP, and we can recover losses, but not in the transport layer, however, in the application layer. Oh, time for a little quiz. Well, in our case, in a smart grid, we said that we have some PMU measurements. So these PMU measurements are in real time. You might have a new PMU measurement every 20 milliseconds, and you need to, in real time, stream it to the PDC, to the control center. We have a real-time streaming communication here. What is the protocol that you will use? It is TCP, UDP, either, doesn't matter. So I invite you to join the speak up. For those of you who does not know what a speakup is, you can use the web interface, web.speakup.info, and you can join this room. Oh, let me open the poll. So as I said, it's anonymous, so please participate. Don't be shy. You can even discuss with each other. It's a small crowd, so don't worry about this. So I will close the poll in a second. Well, TCP is a sophisticated one, so it's very tempting to use TCP, right? But it's not true. Well, for real-time streaming, generally we use UDP. And let me explain to you why. Well, as I said, TCP comes at a cost. One of these costs is the latency. Why do we have latency at TCP? As I said, we recover losses. The thing that is that recover losses by waiting for a receiver to send us some acknowledgement. Now imagine that I have a packet that is on the head of the line and I want to send it. So I will send this packet and I wait for an acknowledgement. For some reason, I do not receive this acknowledgement. I wait a bit, I do not receive this acknowledgement. I will retransmit this packet. I repeat this procedure until I receive this acknowledgement. And in the meantime, everything is blocked. I do not send any new packets because the head of the line packets is not reached the destination. At least I suppose that it's not reached the destination. And I wait to recover this loss. This phenomenon is called the head of the line blocking. So it happens in TCP. And it adds a latency to these packets. In a real-time streaming, the thing that we care about is the latency. So when you have PMU measurements, you want them, as long as they are fresh, as long as they are new to be received by the destination. You do not care about some PMU measurements that are completely received and they are in order, but they are too old to be useful. So it's better to have them in time. But at least, for example, out of 50, you might have only 45, but that's fine. It still is useful. If they are too old, they are completely useless. Another example of real-time streaming is when you watch a football match, when there is a live streaming there, you most probably use UDP. I mean, some of the frames might be lost, but our eyes would not even detect it, but the thing is live. Well, that's another example where we prefer UDP to TCP. Could you give me an example where we use TCP? I mean, did you think of an example when you use TCP? Yes. Oh, exactly. That's one of the examples. Well, when you have a message that's very important for you, the receiver will understand it. Use TCP. Could you give me another example? Yes. Web page, exactly. So when you visit a web page, you want to have everything. I mean, you don't want to open a web page and wait for everything to show up. There is only, for example, a smart grid course and everything is not there. Oh, that's another example. Another example, when you send a video to your friends, so it's important that this friend receive this video in order, everything order with the same quality as you have. That's another example that you use TCP. But for real-time streaming, we use UDP. Well, let's move on. The next layer is network layer. Well, the job of network layer is to provide full connectivity between any two endpoints in all around the world. The ridiculous way to do this is direct connections, but simply it is not doable. Even on a very, very small scale network, it's not doable. Still, it's doable on a home office. For example, when you have a home office, you might directly connect most of your devices with a wire, but it's not doable on a network scale. We do it in the internet in a smarter way. Well, the very first computer networks use a method called store and forward. Oh. The way the internet works is really like the posting. So you create an envelope, you create a parcel, you put the message in it, steal it, and write some important information on it, like the destination address, the source address, and some other important things. And you hand it to some intermediate points. These intermediate points, based on the destination address and their knowledge of the network, will hand it over to the next intermediate points until it reaches the destination. Well, at those times, at the beginning of the internet, we do not have routers to do the routing, whereas we use big, huge computers to do routing. So at those times, we use huge computers and as the intermediate points, where they have a forwarding table so that they can forward packets for us. Well, now imagine Bob wants to send a love message to Alice. So create this envelope, put everything in it, seal it, and put the destination address and source address on it. And it will hand it to the first intermediate point, the first big computer that is connected to. This computer, what it does is first receive the whole message, store it completely, recreate it. Oh, we have the message here. Then look at the destination address. This computer also has what we call forwarding table, meaning that is a list of what to do with each destination address. For example, this is the destination address of Alice here. Well, this computer knows that should forward it to the next intermediate point, which is this one. Well, it first store it completely and then forward it to the next intermediate point. The next intermediate point does the same thing. We'll store the whole message completely, depending on the forwarding table and the destination address forwarded to the next intermediate point. And this procedure continues until the message is received by Alice. That's why it's called a store and forward. But it did not survive, at least completely survive on internet, and people moved towards another thing. It's called packet switching. It's probably because that the size of the data, size of the messages that we were sending becomes very large, and doing a store and forward was not very practical. So instead, what people do now is to first they break data into smaller chunks. We call them packets. Their size are usually up to 1500s of bytes. And then each of these packets becomes an individual postcard. So we put each packet in an envelope and we put the address, destination, and source address on each of them so that they can, independent of the other packets, they can reach the destination. So they go through similar things of store and forward, but each packet go through that rather the whole message. Oh, here is a more sophisticated example. It's a more modern and closer to real world. Well, now Bob want to send a love message to Alice, but it's using an email. It's a more sophisticated thing. The network is much, much larger. Now we have routers. So these gray boxes are routers. So we do not use those computers. We use routers. There are small things, but they can handle several connections. Well, what Bob does first, it will break this message to a smaller chunks, in this example, into 3 packets. And each of them will be sent individually to the Bob's mail server. For example, Bob is using epfl.ch and Alice is using gmail.com. Bob sent the message first to his mail server. Interestingly, mail server does store and forward. So the mail server stores the whole message, recreate it, and look at the destination address. We'll see what it's for some user in a gmail.com. So it will forward it to the mail server of the receiver using packet switching. Well, this data is broken into 3 packets and will reach the destination mail server. We do a store and forward again. And whenever Alice is online, this email is reached and is received by Alice. Well, that's a combination of packet switching and store and forward. Between users and mail servers, we do packet switching. At mail servers, we do a store and forward. Have you observed anything special regarding this routing of these packets? I can show you one. Yes. Exactly. So packets with the exact same pair of source and destination might not the exact same path. Oh, first of all, they are, as I said, each of them is an individual postcard. Each of them can reach the destination independently. So the network does not treat them like they are part of the same data. And why do we send them over a different path? Why sometimes network decide to send them over a different path? Because imagine that you have a very large data that you want to send it, even if you break it into a smaller chunks, but all of these smaller chunks use exact same path. It's like sending the whole data over this exact same path. And that path in the network becomes very congested. You're using this path significantly, and that might hurt these other connection using the same path. That might create losses. Specifically, that might create some buffer overflows within this path. Sometimes, because of the load balancing, we might use different paths. So in order to avoid buffer overflow, sometimes we divide to send via another path. Well, packet switching seems to be a better option than a store and forward. We talked about it informally and intuitively. Let me ask you why specifically we prefer packet switching. So I will open the poll. So I will close the poll in a second. Well, there is a tie between A and C. Well, you think that it reduces the buffer required in routers and also increases the capacity. Well, let's see the answer. Well, I will explain the answer, the difference between a store and forward and packet switching in this example. Here, we want to send a packet to a receiver that there exists only one intermediate point, exactly one intermediate point. So the message will be forwarded to these intermediate points and then would be forwarded to the destination. Well, here I'm plotting in the y-axis the time. So the time goes by in this direction. And in the x-axis, we have the distance. Oh, this is the message. When we transmit it, it takes a bit time for each of bits to go from here to here. because anyway, there is a maximum rate that we can send data to a distance. At best is the speed of the light. And this transmission time is called propagation time. Propagation time always exists in network and you could do nothing about it. At best, you can use the optical fibers, which you use send data at the speed of the light. When you send this message and you forward this message, it takes a bit time. And here at the intermediate point, we are receiving it, we are storing it. In our store and forward, when the whole data is received completely here, is stored here, we can forward it to the next hop, which is the destination here. Oh, this is the time that we receive the whole message completely. This is the time that we start sending. So that's end-to-end delay for a store and forward. What about packet switching? It's the similar thing, but we first break the data into smaller packets. At intermediate points, as soon as we receive a packet completely, we start sending it, we start forwarding it. So we do not wait for other packets. So that's how packet switching works. There are two observations. So first of all, the end-to-end delay is decreased. So we receive the packet faster in the destination. The other thing is the buffer required in the intermediate point has significantly increased. Here was the size of the message. Now it's the size of a packet. Oh, that's a beautiful snapshot of, yes?
Just how do you make sure that your first packet is not sent on a congested line and that the second packet might not arrive first?
Yes. Well, that depends. If you are using TCP, as I said, we have sequence delivery, meaning that at the receiver, you wait for all packets of all sequence that will be received. They might be reordered. That's possible. You send the packet sooner, but it will reach the destination later because it's went through a path that is more congested. There's more delay on it. But at the destination, at the receiver, we will take care of this in order. So we do in order. We reorder if it's needed. Any other question? So it's a small crowd. Do not hesitate to stop me whenever you think that you're confused or you have questions. Well, that's a beautiful snapshot of EPFO's network at some point in the past. Here we are showing several devices. Well, these gray devices, we already saw them. So they are routers. And we have some computers. As you see, each computer has an address. Well, this address, why do we need addresses? Because we want to make communication between any source and destination in the world. So you need to know somehow the address of this guy. So these addresses must have some properties. It's like real world, right? When you want to send a postcard to your friend, you need the address of this friend. And this address must be unique, first of all. So there might not be several devices with the same address. So this packet will not reach the destination because there are several options. At intermediate points, we do not know what to do with it. This address must be structured somehow to show where this guy is in the world. Or like our addresses in Switzerland, we have the country of Switzerland. Now you have a estimation that this guy is in a country named Switzerland here in the world. Then you have a postal code like 1015 Lausanne. Then you have a better detailed information. And then you have for example, a street number and the room number, which is more detailed. And so we can directly go to that device. Like phone numbers, IP numbers in the internet are structured. For example, phone numbers, we say any number that starts with 021 is in Lausanne. This is the same thing with IP addresses in the internet. This is version 4. We have version 6. We'll see in a second. In version 4, each address is 32 bits. We have 32 bits of binary addresses. If you write a 32 bits in binary, it's completely unreadable. So what we do instead is we divide these 32 bits to 4 pieces, each piece 8 bits, and we write the decimal version of each piece. It's easier to use hexadigits, but at that time, for historical reason, people thought it's easier to use decimal version. For example, this 128 is a decimal representation of the 8-bit that corresponds to 128. Well, when we have 8 bits in binary, we can have values between 0 and 255. So each value of these pieces is at most 255. Well, the first thing is every interface of each device has an IP address. As I said, we want to have full connectivity. So each interface must have an IP address. Why I say each interface? For example, when you have a router might have several interfaces. For example, 1,000 interfaces possible. Each of these interfaces must have an IP address. For example, here we have 3 interfaces. Each of them have a different IP address. And each device, if a device has different interfaces, it has different IP addresses. For example, my Mac has a Wi-Fi interface, have an Ethernet interface. They have different IP addresses. And I said these IP addresses must be structured to reflect where you are in the world. Well, at EPO4, this is the case, so like all around the world. As you see, there is a red part in this address set that is same for all devices at EPO4 backbone. For any IP address that starts with 128 is an EPO4 address. So we reserve all IP addresses with the same 16 bits to be an EPO4 address. All devices at EPO4 has this, starts with the same 16 bits, has the same value of the first 2 pieces. But within EPO4, it still is a large company. We have different departments, different rooms. We have to somehow distinguish between different rooms. So we use the rest of the IP address we reserve, for example, in INF 11 something, we reserve the next piece. So all devices that are in INF 11 has the 71 same also. We call these network prefix. So all devices at EPO4 has the same network prefix, has this starts with the same 16 bits. And even in more detail, if we are in the room, so if you look at our addresses, we might observe that our addresses have the same network network prefix. We'll talk about IP addresses more in detail. Well, let's move on for the time being. Well, as I said, we have 2 versions of numbering. The old numbering is version 4. The new numbering is version 6. Version 1, 2, 3 were commercial, never survived in the internet. Version 5 was a mistake. And we have version 4 currently, version 4 and version 6. With version 4, I said we use 32 bits. We have addresses such as like this. In version 6, we use much more number of bits, 128. Could you guess why we are moving from version 4 to version 6? Why there is a need for version 6? Yes? Exactly. Well, exactly. Well, with 32 bits, how many IP addresses do we have? 2 to the power of 32. How much is that? Well, it's 4 billions. So you can only connect 4 billion computers to each other. As I said, every interface of a device must have an IP address. So my Mac has several ones. We all have several devices. We have 4 mobile phone. We have a computer. So it's not enough for the time being. At that time, where people developed this version 4, 4 billions were a lot for them. We had only the internet was several universities with the number of computers in it. So 32 bits was a lot, but it wasn't enough. Now we are moving to 2 to the power of 128, which is most probably is the last version for the humankind. Well, I will talk about version 6. So version 6 is a much more number of bits, so it's even a more chaos to write the IP number. Yes? Well, that's the thing. So we'll talk about the domain. We are moving toward IPv6, but this move is not very fast. You have intermediate points at different points all around the world, and these 2 devices are not compatible. Well, you need to change all devices that are in IPv4 to IPv6 so that you have a complete IPv6 connection. That's why this, IPv4 still exists. It's even more used. Yes, for example, if you have a router that is old, it only supports IPv4. You should change it with a new one. That's, as you can think, is a large cost, and it's hard to. I mean, it's the network is for the whole world, right? You should change all routers everywhere, all computers, all devices everywhere. That's why this change is a bit slow. But we are going through that direction. I mean, now if you buy a printer, most probably only supports IPv6. I mean, we are forcing people to move toward this IPv6. We'll talk about IPv6 addresses, how we represent them, but it's the same principle. For example, for EPFO, every device that has this prefix is an EPFO IPv6 address. But let me talk about another thing. As you see, we have private addresses. We reserve some of the addresses, some of the numbers for private usage. What does that mean? Well, you cannot use these addresses, any address that starts with 10 dot something, or any address that is 192.168 in the internet. You cannot expose this address to the internet. It's not a public address, but rather if you have an experimental network that you want to use privately, you can assign these private addresses. If you have a home network, you want to use it, it's not exposed to the internet, you can use private addresses. There are exceptions. We'll see today that why these private addresses are interesting. We also have private addresses in IPv6. More on IPv6. So we have 128 bits. We divide it into 8 pieces. Each piece is 16 bits. We'll represent each piece by 4 hexadigit. Each hexadigit is 4 bits. So we can have a value between 0 and 15, where 15, for example, is F. We separate these pieces by column, like here. And we prefer lower cases. And there, as you see, an uncompressed version is very long. So there are some compression rules to make the addresses shorter and more readable. The first thing is, in each piece, we can remove the leading 0. For example, here this piece is 0C26. Well, this is a leading 0. We can remove it. That's the first compression rule. The other one, the more sophisticated one, is whenever we have consecutive pieces of 0. Here I have 4 consecutive pieces of 0. I can replace them by this. So whenever you see this in IPv6 address, there are a number of pieces that were in 0, and they were replaced by this. So you count. So here I count. I have 4 pieces. There are 4 pieces missing. Therefore, there are 4 pieces of 0 there. Back to IPv6 addresses. So I said that there are compression rules. We can omit the leading 0. And if there are some consecutive zeros, we can remove them and do such things. But we are only allowed to do it once, because if we do it twice, we do not know how many zeros we should put at what place. Let me ask you this question. So here I'm showing you 3 possible addresses, and I'm asking you which one is a valid IPv6 address. So I invite you to join the Speak Up and answer this question. The poll is open. I'll close the poll in a second. Well, the majority says C is a valid answer, which is the correct answer. And let's see why. Well, obviously, the first one cannot be the correct answer because we said that there are 8 pieces in IPv6 address. Here, we only have 4 pieces without any sign of compression. The second one might be a valid answer, but as I said, there are two compression rules applied here. Well, here we have 4 pieces, means that there are 4 pieces missing. So we have 4 pieces of all zeros. But how can I put them here? Well, should I do 3, 1, 3 zeros here, 1 zeros here, vice versa, 2, 2? We don't know, right? That's why it's not 1-to-1 anymore. So that's why we only use this rule once. Well, the third one is the correct one. Well, now we know we should put 4 consecutive zeros here. There are some leading zeros that are missing. So we can find the uncompressed version 1-to-1. Well, what is the role of the internet? The IP, Internet Protocol, as I said, is to connect every device in every world, any 2 endpoints all around the world. That's why we are using IP addresses, and there are some principles that we should respect always. I already talked about some of them. For example, we said every interface has an IP address. If you have a laptop, you might have several interfaces. Each of them has a unique IP address. Well, these addresses are unique, and even better, they reflect where you are in the world, or they are structured in a way that reflect where you are in the world. We see that all addresses at EPFO backbone, it starts with 128, 178. If you go to a room, there is other parts that are similar for all devices in that room. Every packet contains the IP address of the destination. Well, that's because this packet must be reached the destination. So every intermediate point that receives this packet should know what is the destination address, and depending on what the destination address is, do some routing. Well, every packet has an IP address, destination IP address, and that's the end destination. We do not put intermediate destination address for IPs. That's the end-to-end principle of internet. In fact, it is end-to-end principle, meaning that the application and transport layer are running only at the both ends of the system. The intermediate points only go through the network, MAC, and physical layer. They do not run application layers. That's the end-to-end principle. And in this end-to-end principle, we only put the destination IP address on each packet. Now you're an intermediate point, you receive a packet, you have to forward it. You know the destination address, you need another thing that is called forwarding table, routing table. So you have a knowledge of the network, you obtain this knowledge in some process, and now you know for each IP address where you should forward it. And to do so, we do what we call longest prefix match on the address of the destination. And I will explain to you what this longest prefix match is on this example. Here, we have 3 computers, Lisa, Homer, Bart, and I'm showing you their addresses. Well, these are dummy addresses, but the address of Lisa is A.H1, the Bart is B.D.H2. Well, they are dummy ones, well, but you can think of IPv4, IPv6 address, the same principle applies. We have 4 routers in the middle. For each router, I'm showing you their forwarding table. Forwarding table is nothing but forwarding table. We have different lines. At each line, we say any address that it is B dot something, is B dot some other bar. We will output it at the interface number 2 at this port here. If the address, for example, is A dot something, we will output it at this interface number 0. Then when Lisa sends a packet to Bart, as I said, it will put the destination IP address on the packet. When R1 will receive it, it will match this address with each line of the forwarding table to see which line matches this address. So the address is in fact B dot something. It matches the first line. It does not matches the second line. Well, it means this router R1 will forward this packet to the interface number 2. Therefore, this packet is received by R2. R2 does the same thing. It will match the destination IP address with each of its line in its forwarding table. In fact, it matches 2 lines. Well, the line 2 and 3 both matches this address. This address is both B dot something and is also B dot D something. So what would we do in such situations? So we do longest prefix match, meaning that we use the most detailed line. The longest prefix in the line that the prefix that matches this address is longer. in this case is line number 2, and therefore we will output it in at port 2, and it will reach the destination. We do not output it at port 3. Time for a little quiz. So I did a bit modification here. I changed the forwarding table of R2, and I'm asking if we want to send a packet to Homer, how R2 wrote the packet. Let me open the poll. Oh, if you're answering B, I would like to correct you because we do not have B dot something. Also note that it's possible that the router drop a packet. So if there is no line that matches the address and there is nothing to do, we drop it. So let me close the poll. Oh, there was a unanimous on C when matching the store. So in each router, what we do is most of the time we have what we call default gateway, meaning that if none of the lines in the forwarding table matches this address, or there is a line saying that if otherwise do this. So here at R2, we have this if otherwise, well, line 3, meaning that every other address that does not match the lines above, we will output it at interface number 3, which in this case, the address of Homer includes the other addresses. Well, it is b.c. something, it will not match the others, and it will be outputted at interface number 3. If there were no default gateway, this router would have dropped it because no lines matches, and we will drop it. So default gateway are your last chance somehow. Yes.
What's an interface?
In a computer, well, you have an Ethernet interface, you have a Wi-Fi interface. But if you connect your internet to a computer using an Ethernet, you connect your computer to another computer using Ethernet. That's one interface. Yes. Correct. Yes. Well, forwarding tables, that's true. Well, that is true. Sometimes you update the forwarding tables. Sometimes you can do even more sophisticated thing. You can force a packet to go through some routers. We do not talk about them in this module. Is, as I said, we do not go in depth. In breadth, the only thing that you should know is that we have forwarding tables that does the forwarding. Sometimes we do more sophisticated things because of several reasons, maybe political reasons. For example, you do not, your packets go through a country, you force it to do not go through this country. Sometimes you force packets to different take paths or do not take some specific paths. That's possible. Yes?
Routers are like physical things. So
Right.
you're going to take the path.
Physical or software, both possible.
Like myself, I try to take the path which is closest to your, like the last route should be the one closest to your.
Well, the way that these forwarding tables are obtained by routers, there are multiple algorithms for that. So there is a configuration phase. When you make a network alive, or everything is, every caches are empty, there is no forwarding table, devices go through a configuration phase to have a knowledge of a network, what are the devices that are connected to, how can you do the routing. And in that configuration phase, they will create these forwarding table based on some algorithms. For example, one can be shortest path.
So if I open my laptop in India and Switzerland, it's going to update the forwarding table of the closest route?
Well, it will not update the forwarding table of the router, rather it will update its own forwarding table. our devices, every device, that's the first principle of IP, every device have a forwarding table. For a router is a big thing, it includes several lines. For our computers, includes mostly 2 lines. We'll see what those lines is. One of them is your default gateway. Most of the time is the first router you will connect it to. So when your computer becomes online, it finds the first router that is connected to, and through that router, it can be connected to the internet. We'll talk about it later. I promise it will be more clear. So we do not use routers inside a LAN. So what does LAN mean? LAN stands for local area network. It's also called subnetwork. That all devices that they share the same network prefix. Here I have 2 LANs. At the left interface of this router, I have 1 LAN. So all devices in this LAN, including the interface of the router that is in this LAN, share the same network prefix. In this example, it is the first 24 bits of the IP address. We say these devices are in the same LAN. Why do we care about this LAN? Well, because if B wants to communicate with E, well, if B wants to communicate with a device that is in the same local area network as B is, well, it is directly connected. Well, we can send the packets to this device directly. We do not have to go through a router. We are directly connected. Well, if we want, our computers wants to connect to each other, send some packets to each other, since we are in the same room, we most probably on the same LAN, we can send packets directly to each other. There is no need to be connected to a router somewhere at EPFO and that router send a message to you. Same thing in the other LAN. Well, when a computer wants to be connected to a printer, since they are in the same local area network, they share the same network prefix. This packet can be sent directly. Otherwise, if W wants to send packets to a device that is not within the same local area network, it will go through the routers. So what W does, it will hand this packet to the next router, and the router take care of the rest of the route. Well, as I said, every device has a forwarding table. For a device, we have most of the time 2 lines. The first line indicates your network prefix. That's the way for you to understand what are the devices in the same local area network as you. Well, the first line indicates that all devices that has the same IP address, well, they have the same network prefix, you are directly connected to it. You can send a packet using other mechanism that we will see today. Otherwise, for any other destination all around the world, you have the IP address of the router interface. Well, this packet for sure needs to go to the next router, and from that point, the router takes care of the message. So this is possible to go through several routers. Well, routers comes between 2 LANs. So inside a LAN, we do not use router. Rather, router divides some LAN, local area network. What do we use inside router? We use switches or bridges. So it's an Ethernet connector. It can be a Wi-Fi based station. They're not routers. They say, what is the difference between router? Well, they can be used inside the LAN. They can connect several computers together, wired or wireless, but they are not routers. Time for a small quiz. So W sends a packet to the printer, and here we observe packets. So when these packets are out of W, we look at the packets, and I'm asking what is the IP destination address that we will see. So I open the poll. So I will close the poll in a second. Closing. Well, the majority says A, the IP address of the printer, which is the correct answer. You might be tempted to think that since these devices are in the same local area network, we do not need the IP address of the destination. But do not forget the first IP principle. We always put the destination IP address no matter what. Or even your computers are directly connected. You use a wire to connect two computers. All packets that are sent from your computer to the next computer has the destination IP address. Yes.
There should be both the destination and the sender address.
Yeah. There are other things. So the destination IP address is always this. You see that there are even more. Well, there are even more, and one of them is hop limit, and this is TTL. Well, what's the point of using hop limit or TTL is to limit the propagation of some packets. So you send some packet, and you force this packet to take at most, for example, 64 hops, goes through 64 intermediate points. Why is that interesting? Because there might be some packets that are trapped in a loop. Well, these packets will never reach the destination. They're trapped in a loop. They're going from one router to the other, and they're back to the first router. They are using network resources, but they are useless packets. They will never reach the destination. There are some bugs somewhere such that these packets are trapped. So you want to limit their propagation. So you want to kill these packets that are trapped in the loops or take very long path. We do that by adding, as one of the metadata that we add to the headers of packets, by adding a number, which is the hop limit. So at source, for example, by default, we put the number 64. When a router receives a packet, look at this hop limit. So if it is a number strictly larger than 1, it means this packet can be forwarded. So the router do the forwarding using its forwarding table, and it will decrement the value of hop limit. So it will change the value of the hop limit in the packet header, decrement it by 1, and then forward. If you receive a packet and the hop limit is exactly 1, well, we'll look at it. Or if it is destined to us, it's nothing, we will receive it. If it is not destined to us, it means we have to forward it. We cannot forward it. So because I already go through the number of hop limits that we were allowed, so this packet will be killed. We drop this packet, and we send an error message back to source. How can we know what is the source? Well, exactly. In the packet that we received, there are other information. One of them was the source IP address. Well, when this router wants to drop this packet, we'll say, well, this is the source address. So I will send an error message to this source. And using TTL, we can do interesting things. One of them is trace routes. What is trace route? Well, you want to see whenever you are connected to google.com, wherever you are, what is a path that your packets take? What are the intermediate points that your packets go through until they reach the destination? We can do trace route. We will do it in the lab. Then how do we find out what are these intermediate points? By sending packets with different TTL. So we send a packet with TTL equal to 1. Well, if we receive by the first router in the path, well, the TTL is 1, the packet must be forwarded. What router does is to drop this packet. But it does one more thing. It will send an error message back to source. When we are at source, we receive this error message. We look at the source IP address. That's the address of the first router. Now we have found out what is the first router in our path. Now we send another packet using UDP with TTL equal to 2. Well, now the second router will drop the packet and send the error message to us. Using that error message, we find out what is the second router. By increasing the number of TTL, we will increase it until we reach the destination. So here is an example of trace route to google.com. So it is in IPv6, and you see the last hop is the Google itself. Yes.
But if the routing is dynamic, evolves, and maybe the first one won't be the first one for finding with one.
All right, cool. That's a correct observation. Well, I will answer it in several sentences. First, what we do for each number of TTO, we will send 3 packets. For TTO equal to 1, we will send 3 packets for several reasons. The first reason is that we are using UDP, we are using an unreliable thing. The packet might be lost, the error message might be lost, so we'll never receive this error message. So we will send 3 packets to make sure that this packet, at least one of them will be reached there and we will receive this error message. The other thing is that these packets might go through different paths, and different paths might have different round trip time. So here, as you see at each line, we see 3 numbers, which is a round trip time of each UDP packets that we send for each value of TTO. And sometimes it differs a lot. For example, at line 10, or it's even more than twice, as your friend said. And it's even more sometimes for example, router in the 10th position might be changed because we change different paths. And that traceroute take care of that. So it shows at least one router in the path. The thing that you see at the end is that there is a path there. Well, that might be the only path. That might be there will be several ones. And that's how you can obtain the path. So hop limit is one of the other important information that we put, as well as the source and destination IP address. We already talked about the end-to-end principle of internet. Well, it is end-to-end, meaning that all intermediate points only go through the network, MAC, and physical layers. At intermediate points, we do not have transport layer or application layer. Only at both ends, we have transport layer and application layer. One of the reasons is that to make the internet independent of whatever the application is. So if you have 2 ends, as I said, you and your friend can create your own application and you too only use it. Oh, that's for some reason you do that. But you want to use a internet network for this connection. Well, your application must be independent of how internet works. That's why this application already runs at the both ends of the system. Intermediate points only do the routing and do the forwarding for you. So internet becomes independent of your thing. And there are other aspects. So the performance is better because otherwise you must do a store and forward. And we saw a store and forward has some shortcomings. For example, increase the buffer sizes at intermediate points. And more easy deployment of application, we already discussed. So you can use the internet, whatever the application is, well, perfect. But sometimes we break this principle intentionally for some good reason. We see that this end-to-end principle is not applicable, or we want something more of it, but we'll break this end-to-end principle for good reason. We already see this example. We didn't talk about it at that time. Well, in the mailing example, we will break the end-to-end principle. Well, when A wants to send an email to B, what A does, it will send the message, send this email to its mail server. Mail server will do a store and forward, store the whole message, recreate the whole message, and then it will forward it to the destination mail server. Again, we do a store and forward, we recreate the whole message, and only then we will send it to B. I'm asking you, why do we do that? Why don't we do a direct connection from A to B? We can discuss, it's not a speak up. Yes. That might be true, but that's not the main reason. Well, security is not the main reason for doing that. We can even have an end-to-end communication that is secure. In the mailing example, that's not the main reason.
That may not be online at the same time.
Exactly. So, well, how do you, to have a direct connection to someone, to the receiver, that receiver must be online. If this receiver is not online, it means it does not exist in the network. but you cannot send an email to someone that does not exist in the network. If we do not have, if we do not put mail servers, it means if you are waiting for an email, you must be online 24 hours, 7 days of the week. Otherwise, the message will not reach by you. Well, that's a limit, very restriction. It's a limitation to the people. So to increase the mobility of the receiver, we use mail servers. These mail servers are always online. They will wait for always messages. When the mail server of the receiver, this example here, Y, store the message that is for B. Whenever B becomes online, it will deliver it to you. Whenever you're connected, whenever you turn on your Mac, you see that there is a part that your mailing system is waiting for checking for new messages. That's the part that we will ask the mailing server. Now I'm online. Do I have any new messages? And the mail server provided for you. That's one example. When we break this end-to-end principle on purpose to increase the mobility. There is another example, which is a very nice thing, is NAT boxes. NAT stands for Network Address Translation. NAT boxes enables us to reuse the same IP address several times, specifically using private addresses. Oh, that's against the IP principle. I said that these addresses must be unique. And moreover, if we use private addresses, we should hide private addresses from the network. We cannot expose a private address to a public internet. Oh, that's the job of NAT. Most probably, if you are at EPFO or you are at home, you are behind some NAT. So what NAT does is, behind the NAT, NAT gives you private IP addresses. You have private addresses there, but NAT will hide these private addresses from the internet. So from the internet point of view, you are talking to a public operator. Every device in the internet think that they are talking to a public address, which is the address of the NAT. However, they are talking to one device maybe behind the NAT. So NATs are one of the reasons that IPv4 survived until now, because it enables IPv4 addresses to be reused several times. For example, inside the company, we might have a huge network, but we can easily assign IP addresses to them. We do not have to ask someone, for example, IETF person, that give me a block of IP address, public IP address. Rather, you use some NAT, and behind the NAT, you assign private IP addresses without any constraint. Well, the job of NAT is to understand the correct corresponding behind the NATs. So whenever there is a connection, there might be several people at your home connecting to internet. They are doing different things. One of them is watching Netflix, one of them is listening to a Spotify. There are different connections with the internet. And the job of NAT is to make this correction. So whenever there are data coming from Netflix, and I should assign this data, send this data to the correct corresponding. So how does we do that? Well, NAT creates a one-to-one mapping. It's called NAT table. But if you want to do it only with the source and destination IP addresses, it's not one-to-one. For example, in this example, we have one public IP address for the NAT, and two devices are behind the NAT. So if we do if I only want to use a pair of source and destination IP addresses, it is not one-to-one. So we have to use another data. What's that? Well, that's the port number. We'll see next week on transport layer, when you establish a connection, there is a source and destination port number. You use sockets. In the socket interface, we use sockets. When you create a socket, when you connect to another socket, when you create it, you are assigned to a port number. That's the source port number. And in the destination, there is also a destination port number. And we put them as important things that we said to the packets. So when NAT receives a packet, it sees two things. It sees several things, but two things that are important for us: a pair of source and destination IP address, plus a pair of source and destination port. And using them, it can do the one-to-one mapping. How is that? Well, imagine the NAT table is configured somehow before the connection. When you start the connection, NAT table configure is NAT configure is NAT table. Now the NAT receives some packet where the destination IP address is the public address of the NAT plus a port number. Then it will look at this NAT table, so whatever coming from internet with this public IP address and this port is the same to this private address behind me and this port. So then you can find the correct corresponding. If there is another packet for the other device, we do the same thing. We match it with one of the lines in the NAT table. There might be several processes running in one computer. This computer B might be streaming a video on YouTube or also opening a web page on Moodle. Several other connections might be there. Another usage of port number that we'll see next week is to distinguish between different processes between one same server maybe and same receiver. Might be connected to the same server for different services, different processes. Using port number, you distinguish with them. We'll talk about it next week. Yes. Yes, that depends. I mean, for servers, yes. For example, if there is a famous server, for example, we'll see the DNS server, the port number are fixed. All people connect to the same port number. But whenever you want to connect to a server, you need the destination port number. So somehow we should know it in advance. We make them public. But when you create it on your own computer, the port number can be an arbitrary value that is assigned to you at that moment. If you create another process, you have another port number.
So basically, the compound made of the NAT IP address and the port is basically a temporary IP address for the computer.
Well, the IP address is different from the IP address. The NAT gives you a private IP address. It might be fixed over some time. I mean, as long, for example, your device is connected and is online.
But this one is private.
It's private.
And if you have NAT IP address, it gives you an address to the computer, but which is public and temporary.
Correct. Correct. Well, the thing that NAT does, I mean, it hides the fact that it's giving you private addresses. From internet point of view, they see that they are talking to a public address, one public address sometimes. For example, here it's one public address, but they're in fact talking with several private addresses behind the NAT. NAT hides this fact. To do so, it breaks this end-to-end principle, right? It's because you have to look at the packets and then deliver it to the correct correspondence. Another example that we break this end-to-end principle, as you said, is security. So we have a user, we have a web server, and we put, for example, an HTTP gateway, a web proxy in the middle. Why do we do that? Because all clients around the world can send some requests, send some packets to this server. Some of them are not authorized. Well, because of the security reasons, some requests are not. For example, you have a server for the bank and people might request for a banking account of some other person. So it's not an authorized thing to do. So for those unauthorized messages, you would like to have a security. So we would, before giving this request to the server, you want to look at it, whether it's an authorized one, it's not weird, it can be authorized, then I will hand it to this server. Well, that's the job of HTTP gateway, web proxy. It breaks the end-to-end principle. It first look at all the data, or store them completely, look at them. If they are valid, it will be authorized and you will hand it to the server and the response will go back. Otherwise, it will withdraw. Well, one reason is the security. The other reason is to reduce the traffic in the internet. How is that? Well, is to cache the frequently asked documents at the application layer gateway, at the web proxy. Well, in this example, we have a user that asks for an image. Well, this request will be stored by the web proxy, and we'll go through it. Well, imagine that's the authorized one. Then it will ask the server, so I want this image, and the server provides this image. And after that, the web proxy will deliver it to the source. What it does, one other thing is to store this message in the web proxy. It will cache it. for temporarily, or there is expiration date. We do not cache it forever. And if in the meantime that this image is cached, one other user asks for this same image, or even the same user asks for the same image, we do not send a request to the server and ask for the image because we already cached it and we directly provide it. So that's reduce some of the requests to the server. If at some point in the time this image was updated or was deleted from the cache, we will go through the same process. Cool. You all heard? Yes.
How is it decided what do we cache and what we don't? Like, is it
Oh.
systematic or?
Oh, depending on how you cache things. I mean, the easy way to do it is to temporarily cache everything. So whenever you receive a request for a file, you will cache it for an amount of time. If there is another request and you don't have time, you will rewrite it on the oldest thing that you have in your cache, for example. That's up to the web proxy how it's configured. So you all heard of firewall, or firewalls are nothing but this application layer gateway. In the simplest case, you have an intranet, you have an internal network, you have a home network, and you have the public internet, and you want to separate them somehow, such that only authorized traffic will go through and go out. So to increase the security of your intranet, then you can use a firewall is in application layer in both phases that checks access control and security reasons to authorize and not authorize some other packets. If you are in a company like EPFO or one company, you have one other a sophisticated thing. It's called DMZ zone. Is the demilitarized zone. Is a zone that comes in between the intranet and the internet. That's the zone that is exposed to the internet. More sophisticated, you use routers, and between these routers, you use several application layer gateway for different reasons. Like you have HTTP proxy, you have cloud service proxy, different things. That's the more sophisticated firewall. Again, the reason is security. So we see that end-to-end principle is not always applicable. We will break this principle sometimes because of good reasons. One is the mobility in the case of emailing system, security access control in case of firewalls, web proxy, performance, well, internet networking. And internet networking, as you already one of you asked, we are moving from IPv4 to IPv6, but not all devices support IPv4, IPv6, or both. Some of them is only IPv4, some of them is IPv6. So you might have a connection that cannot be done only in IPv6. You do it partly in IPv4, you break it here, and you do another connection in IPv6. That's the internet network. Well, I will steal a bit of your time because we had started a bit late. I will finish this and then you can have a break. Well, we talked a lot about addresses, IPv4 and IPv6 addresses, but we as humans prefer names. We never say that I'm connecting now to 128, 178. No, we say that I'm connecting to EPF4.ch. So we as humans prefer names, and that's why we provide a one-to-one map between names and addresses. So names are also structured. You can see it. But how can we obtain an IP address from a name? Whenever you want to connect to a server for the first time, to a website for the first time, well, you do not know the IP address of this server, well, you should ask someone that does. Oh, that someone is called DNS server. It stands for domain name server. DNS servers are public, and they have mapping of all IP addresses and names. For example, in this DNS server, it is written that this server of EPFO has this IP address. And whenever your computer is configured, it must have an address of a valid DNS server. This we will see in the lab. If it doesn't have a valid DNS server, you cannot even ping google.com. If the address of Google is not cached in your computer. So whenever a user clicks on ssc.epfo.ch, well, the computer must find out who is this ssc.epfo.ch. Well, it will send a DNS request to the DNS server. The request is very simple. You, literally ask, who is this ssc.epfo.ch? The DNS server will receive this message. It will say that someone is searching for this website. So I have it in my my repository. Well, I will send a DNS reply to this guy. Well, this is the address of this website. How can DNS know IP address of the source? No, that might be true, but exactly. So in the DNS request, they put also the source IP address. So when DNS receives a request from someone, it knows where its request comes from. So the DNS knows the source IP address, but we can send a packet to the destination of the user. Now this guy has the IP address of the web server. Now we can send a request to get a HTML web page, and you see the HTML web page there. Well, until now we went through the application, transport, and network layer. I said to use both network and MAC for interconnecting systems to drawing the path. And we said we'll see why do we need both network and MAC, and that's where MAC layer or link layer, they are both the same things, or the layer that interconnects a small number of devices without any configuration, specifically without going through a router. Well, these devices are connected at the MAC layer. All devices in the same local area network, in the same subnetwork, are connected over the MAC layer, where we use MAC addresses. MAC stands for Medium Access Control Addresses. Is yet another address. What is MAC addresses? Well, MAC addresses are 48 bits of address, where it is unique and fixed for a life for any device. So when your Mac was manufactured at the Apple, they assign a valid MAC address to this device. That's a unique that comes for your device. It's a hardware address, and it will never change. IP addresses will change. So if you move on from one going to another, if you move to another company, your IP address will be changed. As I said, the IP address reflects where you are in the world. MAC addresses or hardware addresses assigned to a device fixed for the life of the device. When we have several devices that are in the same local area network, they can send messages directly using the destination MAC address. For example, if A wants to send a message to this router, if A knows the destination MAC address of this router, it will send this message and put the destination MAC address to the packet, add the destination MAC address to the packet. The difference is everyone hears this message. Everyone hears that there is a message that is coming up. So what every device does, it will check the destination address, or whether it is my MAC address. If it is, so I will have to receive it. Otherwise, I will drop it. So that's why we connect only a small number of devices that are close to each other. I mean, our computers can be connected in the MAC layer because you send message to all devices there. You broadcast the message, and only the receiver and the correct corresponding receiver will go through this packet. The other will drop it. Well, we talked about local area network or LANs. So we say we do not use routers inside local area networks. For example, we use switches or Wi-Fi station. And a local area network means all devices, set of all devices that share this exact same network prefix. The number of bits, I mean, all IP addresses in that LAN, it starts with the exact number of bits. The number depends on the LAN. And if you want to connect two LANs together, we use a router. So, and we see a forwarding table of a device. Well, forwarding of a table of a device has two lines mostly. one line to know what are the devices that is directly connected to. So whenever you want to send a packet to a destination, you check whether this destination is in the same LAN as you. If the network prefix matches with the network prefix of the LAN. Whenever else want to send a packet to this mobile phone, we'll check the destination IP address. If it is in the same LAN, it will send a packet using MAC layer, using MAC addresses. Otherwise, it will use IP using by sending the packet to the router. Well, that's why every machine must know the IP address of the next router. Otherwise, you cannot go out of this LAN. There is another thing called network mask. Well, we see that not only the IP address is important, there's also another thing that is important is to know when this network prefix ends. So whenever you have an IP address or whenever you have a destination IP address, you can distinguish between the part that is a network prefix and the rest to see whether this device is in the same LAN as you or not. So whenever we denote an IP address, we most of the time show the number of bits that are used in the network prefix. For example, this is the IP address, /21, meaning that the first 21 bits of this IP address is the network prefix. Then if you have a destination, you check the first 20 bits of this destination address. If it matches yours, it means that guy is in the same LAN. You use the MAC layer to send the packet. Otherwise, you have a router, you send the packet to a router. For some historical ridiculous reasons, people use network mask. Well, network mask is a stream of 32 bits. The values of 1 indicates where the network prefix is. Well, if you have 21 bits, we put 21 1 and the rest is 0. Then we have a completely unreadable thing. We do the same trick as we do with IPv4 addresses. We divide it into 4 pieces, each is 8 bits, and we use the decimal representation. Or we have 255, 255 means you have 2 8 pieces of all 1, and 248, which you should find what is the binary representation of 248 in 8 bits. Then you have the network mask, which you can use to find the number of bits that must be equal, must be exactly the same as you, or if you're in the same LAN. So whenever you have an IP address, you have a mask. Yes, you see in the LAN. But if you check your IP address, you see also a mask that's to distinguish all devices in your same local area network. So IP addresses changes, and moreover, whenever you want to find the IP address, I said that there is, for example, there are protocols. You can ask a DNS server that what is the IP address of this guy, and the DNS server will respond to you. MAC addresses, however, are fixed for a device. So if someone now comes in this room with his or her computer, we do not know what is the MAC address of that device, because that comes with only that device, and wherever he or she goes, the MAC address is fixed. So there must be a protocol to find the MAC address of all devices that are in your same LAN, local area network. And the protocol is called Address Resolution Protocol, ARP protocol. As I said, the thing in the internet, or you can think of how you can find the MAC address of the destination. And if you look at the things that is implemented, you see it's very similar to the thing that you guessed. Well, you are in the same local area network. Imagine that we are in the same room. I want to talk to Alex. Well, I want to see who Alex is. I shout that I like to talk with Alex. So if Alex is in the room, will respond to me that I'm Alex, then we can talk together. That's the same principle here. The good thing is we reserve one MAC address as a broadcast. Well, an address that is all one is a broadcast message, meaning that we will broadcast it to all devices that are in your same local area network. When you broadcast a message to all devices that are in your same local area network, that I would like to know the MAC address of this guy with this IP address. If you know the IP address of the destination and you ask for its MAC address, Will everyone receive it? Only the one that is the corresponding corresponding end of this ARP request will respond to you that this is my MAC address. How could this guy only respond to you? I mean, how does he know your MAC address? Exactly. In a header, it's the same principle. In the ARP request that the sender sends, the source puts its own MAC address on the packets because the receiver can respond to you directly, or the receiver respond to you directly using your MAC address. Well, this is my MAC address. Now this device knows the destination MAC address. Now sends packets directly to this. Well, it's for such reason. Whenever we want to broadcast a message, one example is ARP request. We want to find the MAC address of someone. You know the IP address, but you don't know the MAC address. From the IP address, you know that this guy is in the same local area network. Then you shout, you broadcast, everyone hears your message that I would like to know the MAC address of this IP address. Sorry.
Because we said there was a MAC address per device.
MAC address is per device.
So this additional MAC address with ones.
Well, I don't understand what does it mean to have additional MAC address. Well, MAC address of our device. Well, we have 4 devices here. They have 4 MAC addresses. Yeah. This device wants to communicate with this one, so it needs to know the MAC address of the destination. It knows the IP, but it doesn't know the MAC address. From the IP, it figure out we are in the same local area network. That's why we will go through this ARP protocol. We will ask everyone who knows this guy. The corresponder will receive you, oh, that's me with this MAC address destination. Now we can talk. As I said, it's like shouting. I would like to talk with this guy, and if he's there, he or she is there, we can go now talk him directly. The last layer is the physical layer. Is nothing but to convert these bits in a form of a physical wave, electromagnetic waves, optical wave, to go through some distance. So most of the time is requires encoding and decoding. And if everything goes low at the destination, when you do this decoding, you have the exact same stream of bits that you send. That's the only thing that we will learn about physical layer. Let's put everything together. We went through all layers one by one. Let's put everything together on a simple example. Well, this example we already saw. Well, we have a web server now wants to send a file to Elaine. Imagine the part that Elaine send a request to this web server is already done. Well, this web server knows what Elaine wants and who is this Elaine, and now sends a file that Elaine requested to her. Well, this file might go through a switch and a router. And let's fix the ideas. What is a switch and what is a router? Router for us is a system or a program, either in software or hardware, that forwards packets based on IP addresses. So we look at the IP header and the forwarding table of the router, includes some lines recording the IP, and you see that it does longest prefix match. Switch or a bridge, for me are synonym, is a device that forwards packets based on MAC addresses. Well, switches, they're either Ethernet hub or a Wi-Fi based station. They are inside the LAN, and as we said, inside the LAN, we work with MACs. We work with MAC addresses, and switches actually forward packets on MAC addresses. What's the difference between switch and bridge? Nothing. But if you like, people tend to call bridge something that is developed in software, switch something that is hardware. So that's a big picture. Well, web server wants to send a packet to a lane and goes through a bridge and a router. Let us start. Well, in the application, we do a send command. What is S2? It's a socket name. Well, we see next week. So we create a socket and we do the send command and we put the data. This application layer hands this to the transport layer. What transport layer does with it? Well, probably it's a large file, so it will break it into a smaller chunks. Here into 3 segments. So it will create 3 segments, and it will hand them to the network layer. Network layer, add some headers on it, create IP packets, add some IP header to this packet that contains the source and destination IP address, you observe time to leave, the hop limit, and some other important thing. And here, what is the destination IP address? I mean, at this level, we use what IP address as a destination IP address? Oh, is it end-to-end connection? So IP address is always the destination IP address, which is the IP address of the lane. Here, we do not put the IP address of the router. As I said, it's an end-to-end communication. Each packet contains the destination IP address, and that's the end IP address. That's the receiver IP address. Then we will hand it to the MAC layer. MAC layer adds a MAC frame to this packet, adds the MAC header to this packet, and creates what we call MAC frame. These MAC headers contains the source and destination MAC addresses. I will ask you now a question. What is the destination MAC address at this point? What MAC address we use as a destination? The switch? Yes? Oh, MAC addresses are local, right? MAC addresses are used in the same local area networks, so they are not end-to-end. Destination MAC addresses changes when you go from one LAN to another. But what we put here is the destination is the MAC address of the next hop. Here is the bridge, or we can say the router. Both are correct. So we put the destination MAC address, which is in this case is the router or the bridge, because this device, this packet is destined to outside this LAN, so this packet must go through a router. We use the MAC layer to reach this router. When we use some form of physical transfer, for example, electromagnetic waves, and these packets are received by the bridge. So these are exactly the same packets that are here. The bridge forward packets based on the MAC addresses, or the bridge look at the MAC frames, what is the destination MAC address, and there is a forwarding here. Whoa, I have to forward it to the router, or we do again, forward it to the router. Well, the router look at the destination MAC address. Well, we'll see what's my address. It's for me. Well, I will read it. A router forwards packets based on IP, so it will look at the IP header. So since the MAC address is destined to this router, it will look at the IP header. We'll see, okay, it's for a lane. A lane is that LAN. Well, I have to send it here. Well, the router changes the MAC address. So now router is in both LANs. Change the MAC address to the MAC address of the lane or that wireless thing. The packet will be received by that wireless thing and says, well, it's for me. I will hand it to Elaine. Elaine look at the IP header. So this is a packet for me, the destination IP address for me. So we have the TCP segments as we have here. Now we do a read command. So now we have 3 chunks of data. Now we want to put everything together to have the file. We have to do read, and that's the socket number that we have here. We will talk about it. Well, that's a very optimistic view of putting everything together, because we are assuming that nothing is lost, right? If something was lost, that was another story. Yes.
Address is changed for the server. The bridge updates the address of the read.
Yes. Well, as I said, bridges. What bridges does? MAC addresses are local. I mean, you put the MAC address of the next hop, for example. But the bridge read this packet. This is a packet that must go outside of the thing, or I should put the MAC destination address of the router. But they put all of them in red because they're the same thing, or there is a process there. Well, the MAC address, we think they are the same because they are in the same LAN. Now it is changed to yellow because we are now going to another LAN. Yes.
How the first network IP knows it's not the same. Like it doesn't need, it cannot use MAC.
Oh, that's a very good question. Well, as we said, every device knows its own IP address and what is the network prefix for, the network mask that we said. Well, this web server will first check the destination IP address of the lane, whether they are in the same local area network or not, using the network mask, and you see it's not.
So the IP address knows that from the IP address.
Exactly. Yeah. And that's why then you use the MAC address of the router, because that's the default gateway of you. You want to go out of this local area network. Let's fix some terminology. I was thinking, yep.
Just a question, how the router has the same LAN, if I understand correctly, but the web server and the receiver, because here we have orange and red. So means they are the same LAN, but
Oh, that's a great question. But routers comes between several LANs. I mean, that's the point of routers. You have a router that has one hand in one LAN and another hand in the other LAN. These, I mean, router has different interfaces. Each interface of a router is in a different LAN. So a router, he's both connected. I mean, he has an interface that is connected to the right LAN and an interface that's connected to the left LAN. And based on the IP address, he knows, I mean, the information of all both. I mean, that's the point of routers to go through different LANs. Well, I was being careful to use the correct terminology. We have several things here. Well, here, when we break, I mean, when transport layer break the data to smaller chunks, we'll call them segments. Well, each part has a payload and a header. TCP segment has a TCP payload and a TCP header. The TCP payload is the thing that might be encrypted, is the data. TCP header are the source and destination port number, for example. There are a lot of information in it, but at this point, we know the sockets at the destination and the port, so we know the port number. Then, after traversing the IP layer, we add other metadata, IP header, including the source and destination IP addresses, and we call what we and we create what we call IP packets. And after handling this to the MAC layer, we add the MAC header, the destination source and destination MAC addresses, and we create what we call MAC frame. And let's take an onion view of this thing. Well, if we capture a packet at the interface of a router, and then we have a MAC frame. Well, at this point, we have a MAC frame. This MAC frame is nothing but a MAC payload and the MAC header. Several important things, source and destination MAC addresses and other things. What is this MAC payload? Oh, that's a IP packet encapsulated in a MAC frame. Oh, MAC payload is an IP packet. IP packet is has yet another IP payload and IP header. Source destination IP addresses, time to leave, and some other information. Then what is the IP payload? It is a TCP segment, where we have a TCP payload and a TCP header. TCP payload can be, for example, an encrypted data of an HTML web page or encrypted data of a video. So that's a view of a packet that is captured and prettily displayed. You see different headers. So we see the TCP header. You see that we have a source and destination port number, some other important information. Then we have the IP header. We have source destination IP addresses. We have the time to leave, the hop limit is 64, for example, here, and some other information. And we have the MAC frame. For example, it's also called Ether header because, for example, we use Ethernet. There we have source and destination MAC address. You'll see, and in the lab, we use Wireshark to capture packets. Who can capture packets? Go through the what are the headers, what are the data, and we will do this in the first lab. Time for a little quiz. Well, at point observation point 1, well, the data is now reaching the router. We look at this packet. What is the destination MAC address and what is the destination IP address. So I open the poll. Oh, here I mean both A and B. So I will close the poll in a second. So the majority says A, which is partly true, in fact. But the correct answer is C. So both A and B are true. Oh, the destination IP address, as I said, is always the receiver's destination IP address, is the address of a link. But MAC addresses are local. And at that point, the destination MAC address is the router's MAC address. If you answer A, you're partly true. Well, the destination MAC address is the MAC address of the router. However, the destination IP address is also the destination IP address is also the end system, I mean the receiver, which is telling. Yes. Oh, that's a great thing. Well, I thought that I wrote lane. Well, perfect. So the majority is correct. Well, that's a good thing to catch. Well, destination IP address is always a destination IP address, which is a lane. It's not the router. However, MAC addresses are local and we with the router. Oh, it seems that you all got the same thing. Congratulations. Well, we put everything together. Let's go through an example that is related to a smart grid. It's somehow similar to the first quiz that you went to take. Here we have a network. We have 3 PMUs and we have 1 PTC. We have a DNS server, we have a router, we have other devices. And PMU A wants to send a packet to PTC. So I wrote the IP addresses. All these are private IP addresses. Oh, this is a private network. We do not using internet. Or this is dummy example. I mean, even the DNS server is private. But that's just an toy example. Every device has an IP address, and PMU A wants to send a packet to PTC. Oh, imagine that everything is fresh. Every device that has come alive and the caches are empty, and we do not have any information of the network. And now PMU A wants to send a packet to PTC. And here at the switch, we observe the very first packet. Like at this point here, I am asking what is this packet? It is a DNS request, it is an HTTP request, it is an ARP request, no? So I open the poll. Let's don't be shy, it's anonymous, please participate. Oh. We have a number of quizzes actually here is a consecutive number of quizzes. Well, if you don't know, you can talk with others. I will close the poll in a second. So let's see the result. Well, the majority says it's a DNS request. It's a good guess, but it's not correct. So let's see what's the correct answer. Well, the correct answer is the ARP request. Why do we need it? I mean, what MAC address we need to resolve that we use ARP here? I mean, what's the point of using ARP? Because ARP are a protocol that we use to find the MAC addresses of all other devices. What's the point here? Why can't we just send the DNS request?
DNS is to ask if the name is valid. So it's already in the public network.
The DNS mean?
Yeah.
Well, a friend is saying that the DNS server is, if I put it in other words, it's another local area network. But that's what you mean from the public internet?
And there's a router in between, so probably.
Well, the thing is, well, let's say, well, we want to do a DNS request, right? But the DNS server is not in the same LAN as you are, right? Then we have to go through a router. But when we put everything together, we observe that we need the MAC address of this router, right? At this point, we create a MAC frame where the destination MAC address is the MAC address of the router. I mean, even in a simpler case, even if the DNS, in a very toy example, if the DNS was connected to this switch here, it was in the same LAN, the first packet was an ARP packet because we have to resolve what is the MAC address of this DNS server. So whether the destination is in the same LAN as you or it's not, the very first packet that you see is most probably an ARP request to find the MAC address either of the destination or of the router, that the next router that we are connected to. Yes.
If they store the MAC addresses of DNS server,
Well, when you have a computer that's it's been a while that was online, it's connected to the internet. Well, things are stored, things are cached, and you periodically update it, check whether everything is work fine and everything is the same as the time that you configure things. But I told you that this is the very first packet. I mean, everything is alive, everything is fresh, caches are empty. But you're right. After that, it finds the, for example, the MAC address of R1, well, it caches it. Periodically check that whether R1 is alive and everything is going fine, but it will cache things, correct. Let's move on. Well, we do the ARP request, we receive an ARP reply. And after that, we send another packet. Well, another packet is sent by TMDA. I mean, right after that, we receive this ARP request, and I'm asking, what is that packet? It's a HTTP, TCP, DNS, or none of the above. Are you from the poll? So I'm closing the poll in a second. Let's see the result. Well, now DNS is the correct answer. Majority is saying it's a DNS request. Well, PMUA wants to know what is the IP address of PDC. To do so, yes.
And very first, how do the PMUA knows IP address of the DNS server?
This must be configured in a computer. I mean, if you don't have a DNS, I mean, valid DNS address, you cannot, I mean, unfortunately, that's not how it works. You should either know the destination IP address or a valid DNS server. Well, PMUA needs to find the IP address of PDC. For doing so, you should do the DNS request. After going through the ARP protocol, it can now successfully send a DNS request to the DNS server. What is the IP address of the PDC? The DNS server hopefully will answer, reply, and this is the IP address. Oh, yes. Correct. Well, that's true. Well, the packet that the DNS request that goes from PMUA to the DNS is first forwarded by the switch to the router and then to the DNS server. Well, that's my next question. It's not the next question, it's a bit next. But let me ask it now. Well, at this point here, if you look at the packet, what is the source IP address and destination IP address of this packet, of this DNS request? That's your question of your friend. Well, if you look at the packet, what is the source? It's 71. So I open the poll. Well, IP addresses are written below. Well, these addresses are here. For router 1, we have north, west, east, south. So here is R1W. Well, we are looking at a packet that is a DNS request, right? We are still in the case that we are sending a DNS request. We're not sending packet to PDC. Well, I'm closing the poll. So let's see the result. Well, the majority is the correct answer. The answer is A. Oh. The source and destination IP address will not change in the intermediate points. The destination address is always the destination. Here is the DNS, and the source address is always the sender. Routers only forward things. I mean, switches will not even look at the IP header. They will look only on the MAC addresses. Routers only forward things. They will look at the packet that will forward it. They might increment the hop limit, but they will not change the source address. Because it's important, because if something goes wrong in the network, or even nothing goes wrong, imagine nothing goes wrong and the DNS receives this DNS request, then DNS wants to send a reply, right? Then it's important for DNS to know who is the true sender. Well, DNS doesn't care about the router or intermediate points. That's why we keep the source and destination IP addresses. We keep them the same. Whenever you send a postcard, you write your address on it, because if something happened or the receiver wants to reply to you, has your address. We do not put the intermediate address of the post office, for example. Yes.
You said we were always doing end-to-end.
Correct.
So technically, way
Well,
to send it?
well, no, that's not true. Well, we haven't started our end-to-end connections with PMUA to PDC. We still do not know what is the IP address of the PDC. What is the connection that we have now is an end-to-end connection from PMUA to the DNS. And that's yet another connection. That's a pre-connection basically. I mean, when you go through another connection, you ask a DNS server what is the IP address, and only after that you can start a connection with PDC. Right. You had the question.
How does the DNS know that we want to send a message to the VPC?
Oh, in a message that we send to DNS, we need to realize that I want to who is PDC. You put a name. Oh yeah. When you capture a DNS request in Wireshark, if you look at the message, it is who is I don't know, epfl.ch in this example, who is PDC. But at the DNS, we have a table, it's written PDC this one. Well, what is the protocol that we use for a DNS request? It is TCP or UDP. Let me open this. We use a TCP connection to send DNS request to a DNS server or UDP. Well, I'm closing the poll because we have a bit question, so we go a bit faster in this question. So I'll close it at the time that the majority is correct. Well, is UDP? The answer is UDP. As we said, it is a case of a single message. The DNS request is a case of a single message that requires an answer. For such cases, we do not go through the complicated TCP. We use a simpler, an easier one, UDP. We send a single message. If it is lost, I mean, if we do not receive a reply from DNS, whether the request or the reply is lost, the application layer will retransmit the thing. I mean, we'll recover the loss anyway, because we are waiting for this address. If nothing happens after a while, we will send another DNS request. That's why we use UDP. Well, in this DNS request, what is the source MAC address and destination MAC address? If we capture a packet like here. Let me close this. Oh, no. So the observation point is here. Oh, I'm closing the poll. Well, the majority says C, which is the correct answer. So as we said, MAC addresses are local. Destination MAC addresses changes. Here we put the destination MAC address is the R1W is here, and the source is the PIN.
You have to put the MAC address of the switch,
Yes.
and then you switch.
Oh, we do not change the source MAC address, the same thing. The sender, it's important to know the sender, not an intermediate point that forward the packet. The sender is always the sender, whether in the MAC layer or at the source. Now imagine that DNS server replies that this is the address of PDC. Yes. W is a west interface of this R1.
You can answer
The DNS server is on north.
Why do we use really for an answer on the DNS server?
So if you do not have an answer, the application layer will transmit the packet, because our computer is waiting for an answer. If time goes on and we do not receive an answer, we assume that the thing is lost, and the application layer asks the transport layer to do the transmission. We do not do this transmission automatically by the transport layer. However, in the application, we will do. Yes.
Would it be possible to have an answer here PMUA, then SW1 north,
SW1.
and then SW1 change to PMUA?
Well, yeah, but the observation point is here. We observe a packet here. Oh. Anyway, yeah. So we pass the bridge.
Yes, but this example, I thought that it was equal for the PMUA to send the SW of the router. It knows that then
Yeah.
to go from the switch on the router.
That's correct, but after the switch, the destination is the router itself. Well, I will skip this question. Well, now we have the IP address of the destination. Now we send some packets, and the thing is here, the application is neither TCP, DNS, HTTP is this guy, because that's the application that is used to send the phase measurements. And then we ask what is the protocol, what is the source and destination IP address of all packets that goes from here to here, and same for MAC addresses. I will skip them. I will directly go through the last question of today. Oh, it is a more sophisticated one. I will give you a bit time to go through it. Well, at R1, I'm proposing 4 forwarding table. And I'm asking which one is valid. How we can check a forwarding table is valid? We check at R1 how R1 handles packets. Well, for whatever packets that is destined here to PMU A or PMU B, we expect R1 to forward it to its west interface. For a packet that has the destination address of a DNS server, we expect R1 to forward it to the north interface. And for any packet with the destination address of either of these devices, we expect R1 to forward it to this right interface, right? Then a forwarding table is correct if it respects all these. So if it can successfully forward all packets to the correct interface. Here we have 4 forwarding table, A, B, C, D, and I'm asking which one or which ones are valid. That's more sophisticated question. Maybe you need to write something down, or you can even discuss with your friends.
The number 8 and 16.
Well, it's like saying that it is 10 dot something. 8 is the number of bits. It's showing the prefix. For 8 bits, we check the 8 bits means the same first one. I mean, the first 8 bits must be 10. Here, the first 16 bits must be 10.1.
Because decimal 10 uses 8.
Yes. It's not always multiple of 8, like we have 13. Or the first 13 bits must be 10 dot something more. We should write the binary. Well, as I said, to answer such question, you need a bit more time. So the correct answer is BCD. I will go through one correct answer and one wrong answer. Well, A is wrong. Why A is wrong? Well, imagine a packet that is destined to the DNS server. So we say whatever that is DNS or okay. Okay. 10.21. Yes. So a packet that has a destination address of a DNS server. Well, this router use this forwarding table. Well, it does not match the DNS server. The address of the DNS server does not match this one because it is 10.10 rather than 10.1. It matches this one, so it's a correct one. Let's look at the packet that is destined to the PDC, for example. Okay, so now I get it. Well, if a packet has a destination as PDC, which is 10.2.1, well, if you use this forwarding table, it does not match the second one, but it matches the first one. The address is 10. something, but we will forward it to the north interface. We will forward it to the DNS, and that's a wrong example of wrong forwarding table. What is the example of correct forwarding table? It's this one. Well, if a packet is destined to some addresses here, 10.1 something, we will forward it to the west. If the address is 10.10 something, such as DNS, we will forward it to north, others to the east. For some of the forwarding table is a bit more sophisticated. As we said, we have, for example, 13. It's not always multiple of 8. You need to write the binary representation of all devices that are in the east side to check whether they have the same prefix as this line in the routing forwarding table. But if you check it, it's the correct answer. And the same thing for the last one is the correct answer. Well, that's it. That's for today. Sorry for the problem that happened. We had to do a bit overdue. And I invite you to do the next quiz and the next lab. And we'll see you on Friday during the lab session and next week. Thank you very much.